Hello, in this video we're in the multiple linear regression setting and we're going to develop a confidence interval for the mean response at a given x and a prediction interval for an individual response at a given x. And as a reminder, the multivariate linear regression or the multiple linear regression model looks like this: y equal to x beta plus some error term, epsilon. The beta is a k plus 1 by 1 vector. Here, since we're developing confidence intervals, we need a distributional assumption. So we're going to assume epsilon is multivariate normal with mean vector 0 and variance covariance matrix sigma squared I. Now, one note here is if we look at the expected value of y with this vector, so there's n observations here, right? And then so that's the expected value of this, because that's what y is. This is constant, so it comes out. That's, expected value, but it's 0. So we're left with this. And this is an n by k plus 1 matrix, and this is a k plus 1 by 1 vector. So this is a n by 1 vector. And so the expected value of this vector is you find the expected value of each component. But that's not what we're doing in this video. That's also clarification for some previous videos. Here we want one observations, expected value of yi. And that is the expected value of xi beta I. And so this right here is a vector. Okay, the first component is a 1 associated with beta 0 in this vector. And then the remaining are, x1, x2, x3, all the predictor variables to try to predict y. So now, we want to do this. We want to estimate, the mean response at a particular x, or x0. And this is it. The expected value of y, given that we're at this x value, and its expected value is this. It's the population parameter, and this is all the predictors, in this x0. So as a point estimate, we're going to use the fitted line evaluated at that x0 point, which is this. So remember, that's our least squares estimate for the beta parameters. Let's see if it's unbiased. So we take the expected value of the fitted line, or I say line in quotes, the fitted equation, given that we're at x0, and that's so the expected value of this, but that's constant, so it comes out. Expected value of this, and that's unbiased, so we're here. Now notice that this is a number, right? The fitted value is a number. Of course, it's evaluated at x0. So this is a 1 by k plus 1 vector, and this is a k plus 1 by 1 vector. So the product is a 1 by 1 matrix, which is a constant. So it's linear in the y's. So this is our point estimate, and beta hat is estimated with this equation here. And if you look at previous videos in the least squares development, that we get this. And so it's linear in the y's. Now the variance of our point estimate, so the x comes out front and we transpose it out back, and it's the variance of beta hat, which in previous videos we said was sigma squared x transpose x inverse. So therefore, since it's linear in the y's, its expected value is this, its variance is this, it's normally distributed with mean this and variance that. Now, if we subtract the mean from this and then divide by the standard deviation, then it becomes a standard normal distribution. But we don't know the population variance, so we have to estimate that. But then it becomes two random components, the fit and x, or the x sigma. But let's estimate sigma with sigma hat, which is the square root of the mean square error. And so then we just plug it in right there. So this right here is this. But we have to rewrite it to find, to highlight its distribution. So we take this piece here and put it in the numerator, and then divide by sigma, which is the population variance. but we also divide by the square root of sigma squared, which is sigma, so those cancel. Now the mean square error, the sigma hat, is the square root of the sum of the squared errors divided by n minus k plus 1. Well, this here is a standard normal distribution, like we said, and this is a chi-squared divided by its degrees of freedom. And so this is a t-distribution with n minus k plus 1 degrees of freedom. Now, the next, we have to see if the numerator and the denominator are independent for this to be a t-test. Okay, but also remember that t is this. All right, so I don't have to flash back on the next page. So the numerator and denominator are independent, because if this is beta hat, and this is the sum of squares residual, and we take this first piece times the matrix here, and it's 0. And now, without perpendicular projection matrix theory that we've been using, you have to multiply this in, and then you can do it, very doable, and show that it's 0. But we know instantly, because that's a perpendicular projection matrix onto the orthogonal complement of the column space of X. So anything in X times this is 0, right? Now, to develop the confidence interval for the average Y at a given X, it's this. So T from the previous page, that fraction or whatever, the number that we got, the probability is between the alpha over 2 cutoffs and the t distribution with n minus k plus 1 degrees of freedom is 1 minus alpha. And then t, and I'll flash it anyway, is this. So we can multiply this to both sides, subtract that to both sides, then multiply by minus 1 to isolate that. And then from there, we come up with a confidence interval of this. It's the fitted value plus or minus t times the standard error associated with that fit, which is this. And that's a 1 minus alpha percent confidence interval for the average Y at a given X. Now, prediction interval is for the next Y at X. And actually, if you remember, if you go back and look at my using R simple linear regression from scratch, when we did a prediction interval, we got a warning saying, hey, you're using all the X's that you used in the fitted model. And please note that prediction intervals are supposed to be used for the next Y. And so you can go back and look at that. So yeah, that's a good point, that it's for the next Y. Now, the next Y, we are hypothesizing that it follows this model plus some error. So the goal is to find a prediction interval, or maybe a confidence interval, for this individual Y. But since it's for one, it's called a prediction interval. We're going to use as a point estimate the fitted line, which we looked at previously in developing the confidence interval for the average Y, right? So Y0, Y naught, is the next Y that we're trying to predict. And note from the previous page, we said the fitted model evaluated at X0 is linear in the Y's. We showed it before, but that also means that it can be written in this fashion for some constant. It's the sum of all the Y times some constant that doesn't involve Y. And so that means that this is automatically linear in the Y's, right? So this piece here is sum from 1 to n, and then here we have Y0. But if we just put that Y0 in that sum and start at 0, then it can be written in this form. So this is also linear in the Y's. So let's find its expected value. That is this. Y is this. So this is constant, so it comes out, and the expected value of epsilon is 0. And this here we showed was x naught beta, and so those cancel and it's 0. The variance associated with each of these, the variance of this plus the variance of this, there's no covariance because there's no y's in here that are in here, and so they're independent. And the variance of the fitted value on the previous page is this. The variance of an individual y is sigma squared. Factor out a sigma squared, and then this is the variance associated with this. Now, I remember when I first learned this, I used to think, why the heck are we developing it for this? Don't we want just this? Like in the confidence interval, we only looked at the fitted value, and then somehow we came up with a confidence interval. But here we're looking at this. And the reason is we're trying to develop an equation that involves this y0, so then we can isolate it and have a confidence interval. So based upon what we just showed, that this difference is normally distributed with mean 0 and variance covariance matrix this. Oh, and actually that's a good point. This is not a variance covariance matrix, it's just the variance, because this is a constant. So if we take this value minus the mean, which is 0, divided by the standard deviation, it's a standard normal distribution. Now if we estimate that sigma squared in a fashion similar to what we did with the confidence interval, it becomes a t-distribution with n minus k plus 1 degrees of freedom. Now, the probability that this t is between those 2 alpha over 2 cutoffs is 1 minus alpha. Then you can multiply up, subtract that over, multiply by 1, and you can isolate y0. And I'm skipping that step. And then a 1 minus alpha percent prediction interval for y is this. It's the fitted value evaluated x0 plus or minus the t random variable times the standard error associated with this fit prediction. And that's it. And that's the prediction interval for the next y. Well, that's all I have for this video. The next video we're going to look at simultaneous inference on all the betas. So hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.